Welcome everyone. This is the second one I've done, so hopefully it will go smoothly. If something goes wrong, you can't hear me, if I suddenly drop out, then Erin will get hold of me and tell me to get back on. And a quick thank you to Rezon up here in Aberdeen, without who I wouldn't be able to do this, as I'm up in Aberdeen at the moment, and very kindly let me use their office to conduct the webinar from. So it just goes to show with modern technology you can do it from anywhere. So what we're going to be covering today is the overview of. I'm going to give you an overview of what we're doing here. We're going to be talking about PFM, what is a PFM, and how to build one, how to become a serial dot killer by manually editing the soundings, and how that works, because sometimes you still need to do that, and also then going on to cube processing, using the cube filter to clean the data. I won't actually unload, I'll just show you how to unload, because it doesn't take that long actually, I might do that. And then a bit of how to, if you're doing nautical charting surveys, how to use the software for that. And then I'm going to demonstrate one of the two ways that you can get Fledermaus from Bathy data from Fledermaus into a database, and show you that one. So what we're talking about today is FM Hydro, the bundle as such, and that's what PFM and the area-based editing and cube is all part of. If you have FM Pro, you get this automatically anyway, but if you have FM Habitat or FM Offshore or FM Viz 4D, then there isn't really like an add-on to get the PFM. You basically get upgraded to the Pro version. So that's how it fits into the scheme of things. And then what we're going to be talking about today is really this top one of how to get bathymetry into Fledermaus to clean it and then get it out again. And then just to let you know, if you didn't already know, that we also have FM Geocoder if you want to use the backscatter processing, if you want to process backscatter data, and we also have FM Midwater, which is the only commercial package around at the moment that will handle water column data or midwater data from both the Rezon and the Kongsberg sonars. So that's the how you can deal with multi-beam data. So what we're going to start on is just area-based editing, point killing essentially, and probably a good place to start is what data types can you actually bring in to the PFM. And these data types are down here on the left. I hope you can see them, but there's a lot of them now. There are some which are Windows only. There's the Caris data, the PDS 2000 data, and also the HiPAC data. They all require us to read through DLLs, and those DLLs are obviously Windows only. So anything else you can fire up in either Linux or on the Mac, depending on which is your platform of choice. There's also issues if you've got 64-bit Windows, because some of those, Caris in theory is now 64-bit on the library, so you can load in the Caris data on a 64-bit system. With PDS and HiPAC, you can run the 32-bit version of Fledermaus to load the data and then use the 64-bit to work on the data. So that's how you sort of get around those, because those are both still 32-bit libraries. So just a little side. And also, of course, you can bring in LAS LiDAR data if you happen to be dealing with topographic LiDAR survey. So so the choice is yours, basically. The PFM, or Pure File Magic, as it is the abbreviation for, this is a file-based spatially accessible disk structure And this was originally conceived at the Naval Oceanographic Office by a very clever chap called Jan Depner. And then it was incorporated in a CRADA agreement that IVS and the Naval Oceanographic Office had to develop it further, and then we're also now working on PFM2 or Son of PFM, or however it's going to be called. But fundamentally you have a surface and a folder structure which allows you to have surfaces and another folder structure which keeps all the soundings, and the two are intrinsically linked. So this is sort of the workflow as such that we'll be doing with 3D editing. So we have to make our projects and bring the data in. We then have to select data, plot that data if you want to, and then down here is actually how we go ahead and do the various stages to work with the data. Oops, that's a little bit ahead. So what I'm going to do at the moment is just quit out of this for the moment and go into DMagic. Some of you have seen the DMagic one. I'm just going to show you quickly how to do this. If you want to create a project, then you can specify the location, specify the name of the project, and then you can specify either one of the common coordinate systems, or you can go into here and specify any of the coordinate systems. This is all the EPSG coordinates, geodetic coordinate systems. One thing to note very briefly, if you can see that with there, there's a 2WGS84 section there. If you do have a datum shift, you need to make sure that those values are recorded in whatever one you're using. So I'm going to you can also load up a recent project here. There's no data in this one at the moment, so I'm going to add my ungridded data. I've got a collection of GSF files that are all stored in one folder, so I'm just making a little wildcard selection, and there are my GSF files here. And once they're in, I'm going to, this is now asking you what coordinate system your source data is from, where these GSF files are from. GSF files are always WGS84. That's actually in the specification, so that's it knows that it's GSF, so it knows that it's that. But just in case you've done something strange with the data, then just make sure this is where the data is coming from, not necessarily where it's going to. So, so I'm just going to finish that. And as the data comes in here, it gets scanned in, and then as it gets scanned in, it gets loaded in. Now, just to quickly show you the PFM, the Fledermaus project structure, when you create your folder, you have a little project XML file, and then you have your history, metadata, and PFMs go in the PFM folder, your SDs go in the SD folder, and the source data. This is where I've actually located my GSF file, so you can put the ungridded data, as it were, into this folder. You can also select another folder anywhere else for using it, so you don't have to be constrained by this file structure, but it can be quite useful to do that. So we now have our lines in here, and if we're just going to create a PFM for the area, we can either select them over here, or we can come into DMagic and select the area here. Notice with this is now 7.2.1a, and you have a nice blue box now that shows you where things were, which makes life a bit easier. Then I'm going to select the whole area, and what I'm going to be doing is building a PFM. So I'm going to select and build PFM. Actually, let me unselect those for the moment, and then reselect them, and then build PFM. It's always when things go wrong. So build PFM. I'm not going to use auto processing queue because that's what I'm going to do on the next bit of the presentation. Now, I made this project up in a UTM zone 30 coordinate system. It knows that the data is in WGS84, so that's why that's grayed out. You've already specified that when you loaded the files in. This is this, say the project coordinate system. If you wanted it something else, you could always create it in another coordinate system. The bounds here are taken from my box around the area there. If you have a large amount of files, you don't have to wait for all the scanning to be completed. You can just say auto scan on load here and then press next, and when it creates the PFM, it will also create the metadata and then create the PFM at the same time. So you don't have to wait for these scanning things to finish, but you would have to scan the data here because it wouldn't know where to go from. There's also a file here, it's a .are file, which is an area file which you can load in. It's not used that much now at all, but you can if you want to. The Z range is also known because it has scanned the data. Now this is something I'll just go back one on. When you create a PFM, you have to do a little bit of thinking about where I am in the processing flow line. If you're going to add data to your PFM at a later stage, then the bounds here need to be the survey area bounds. They don't want to be just today's data. If you're going to have a large project, then your area must be the whole survey area. If you don't do that, then when you try to append data to a PFM later, it's going to be rejected because the bounds it's outside the bounds, so it won't go in. So that's an important point to note. That's also the case for the Z range here. Because this Z range on auto is basically selecting the range of the data that's within the files in DMagic. And if you, again, want to include data which is outside that range, then you need to specify the potential maximum range of the data. It's not a problem to specify quite a large range because it's not going to take up too much space. But if you're doing shallow water work, you know you're never going to be deeper than 100 meters. So do it from 0 to minus 100, and then you'll always be within the range. Don't. One of the things that you have to be careful on in this is if you do leave it on auto, the data can actually go into the to the PFM, but then be rejected because it's outside of the Z range. This is be an important issue, because if it's rejected on the way into the PFM and you go and clean all the data in your PFM, which you think is correct, and then you unload it all back, those points which are outside that range won't have been even touched by the PFM. So you might end up with data that is either too shallow or too deep. So be careful with this. If you have a data that is, if all the files you're going to be working on are in this project at the moment, then you can quite happily put this to be on auto. If you're going to add data in later, then set it to a different size. I'm going to use a bin size of 4 meters. So this is setting the cell size for the DTM, and then the vertical resolution here. This is really how accurate your depth data is. Now, if you're in shallow water, and then you can, and also it depends on your specification. If you have to deliver data to 2 decimal places, then always use centimeters. So for shallow water, that's normally the case. If you happen to be processing deep water data, like if you're 5,000 meters, you're not going to be accurate to centimeters. You're only going to be accurate to meters at best. And I don't know of any sonar at the moment which is accurate to millimeters, so that's just there for the future. So centimeters is what we'll use for this. Then it is possible to add in other attributes. So this is going to color the data set, or you can use and view the other attributes in this data set. For instance, I can say look at the pitch or the roll there and call that attribute 1. So if you're trying to sort out an artifact in your data, then this can be quite useful. So I'll put roll as attribute 1 and heave as attribute 2. And then I'll just select them here. If you need to rename them, you can rename them. And this gives you the range, because when it scans the data, it not only scans the data for the X and the Y and the Z, or the Z for those of you in America listening, it will also scan it for all the other fields that go into this in this data set. And the GSF here, this is looking at the GSF fields that are in there. So not all of them are going to have data in. For instance, I know there's no amplitude data in these ones, but for those records that have got data, it will scan the range of the data. Now this next step is if you want to do any beam rejecting based on beams or based on depth. Quite often you're bringing data in from something like Quincy or HiPAC, which they've already got filters. You might have already used them online. So most of it, it's here because you might want to use it, but on the whole, I would recommend always using them online as much as possible, because the guys online are the people that know how the system's performing the best, and they should be making filter changes there which will reject data based on how they see it. Like if they've got a lot of aeration around the transducer or something like that, they might want to put a 2-meter range filter or something like that if you're on the system, in which case you'll carry that data through. It's better to do that than try and do it here. But if you wanted to do a beam calculate, take out the outer beam, say, then in the PFM scheme of things here we have record and sub-record rather than ping and beam. The reason for this is that you can also use Fledermaus to process LiDAR data, and laser scanners don't ping and beam. They have something else. So you have a generic term. So record is ping and sub-record is beam. So if the sub-record is, say, less than 5, then I'm going to set the rejected flag. I'm going like that, and that will take out beam numbers 0 to 5, or 0 to 4. If I want to do it greater than, and in this case this is a resonance about 8125, so it's got 240 beams. So if the sub-record is greater than 235, then I can add that one too. So so this will take out the outer beams of this particular data set. The one you have to be very careful on is the actual depth one, because it's more of a case of getting, I'm just trying to find where the depth is, it's here. Because with the depth one, you can also do it if it's greater than or less than, but you have to remember that you're talking negative values for the deeper you go. So the minimum value is the maximum depth. So if it's greater than 5, it will take out anything from 0 to 5 meters, and if it's less than minus 100, then it will take out anything. So I'm going to put greater than 35 here, because I know that there's some noise up at the top, and that should take that out. So be careful with that, because that's, and I put it wrong. Let me just remove that filter. Minus 35. So if you're not careful, like I just did, or if you get the greater than or less than the wrong way around, you can completely reject every single point in your data set. So so you have to be awake before you do that bit. And then it's just a question of giving it a name. So I shall call this 1, as this is where we are. And what it's doing now, it's did the initialization of the bin. Now you didn't see that because it's not a big area, so it did it very quickly. And that's basically establishing the nodes and where they are. And now what it's doing with the adding data files is it's looking at the file coming in. It looks at the latitude and longitude of that beam, and then it decides which cell that belongs to, and then it adds that link between the sounding and the cell. If the initializing bit takes a long time, then what's probably happened is that you've got a rogue navigational point in there, and you're trying to create a PFM down to 0. It will never happen if you do the select mode like I did here. You will never get that situation. If you do the full select all the files, then you might have that situation. What it's doing then is basically trying to establish a grid node from wherever you are down to the equator. If you're on the equator, you're lucky, and then you've probably still got some hard drive space. If you're up in the North Sea, you're unlucky because it's trying to do a 1 meter DTM all the way down to the equator. So it'll basically fill up your hard drive until it stops. So if you see it on initializing bins and it's taking a long time, that's the problem. It's got some flyer in it. Now, when you finish this is the operation result. Do not just press OK. This is the only chance you're ever going to get later on to see what the results of the PFM were. We're going to take this so that it logs it into a file so you can actually look at it. But this is important because it's saying we've got a total of what have we got there? Just over 5 million records, of which it's accepted 4.6 and it's rejected 200,000. And this is our percentage. Now, if you had your depth filter the wrong way around, then these numbers would be reversed. And then also here, this rejected data because of the XY bounds. And the XY bounds, you see there's a little bit off the top there, and there's a little bit on the bottom there, and maybe a little bit out the side of here from here. So that's expected. If you've done all the files here and you find that that's like 3%, then that's not expected, and there's something that's gone wrong somewhere in the line. So that's an important one. Same with the depth bounds filter. You know, if you're not expecting to see data being rejected, then by these two, then that's why. So especially if you add data into a PFM later, then and you find that you've got this bounds filter, then its chances are that the data you're adding into your PFM is outside of the bounds that you originally set for the data. So, and the custom filters here, this is my my little depth filter and also my outer beam filter. So then I say OK, and I just click over here for the moment. You now have this red splodge to show you the bounds of that PFM, and you also have down here an SD file, and it's called PFM DTM. Now, to look at this and to run this, we'll go into Fledermaus. You can double-click on it, but I'll just open up the SD file. There's Falmouth 1. So this is our PFM now in 3D, just with the bounding area, and the just to show, we have a georeferencing here as UTM zone 30 as before. You can't change the georeferencing of a PFM. If you made a mistake on the PFM when you loaded it, or the project with the wrong georeferencing, then you have to start your PFM again. You can't reproject all the points in the PFM. You can reproject in Fledermaus the surface once you've done it, but not the actual PFM itself. So to look at the PFM, you can either select an area, because this PFM can be huge. We've had PFMs for like 2 months worth of work, and they're well over 2 terabytes in size and contain billions of soundings. So there is no real limit to, well, I think there is a limit, but it's a very high limit to how big the PFM can be. And then so you don't have to open it all, so you can either extract the selection, this little bit here, or you can go ahead and we can extract the entire area. What we're going to do now, you can then zoom in. I shall wait for the screens to catch up, because sometimes it takes a while. And it's one of the real advantages of using Fledermaus for doing your bathy processing is, I mean, it's not hard to see where you've got issues with the data. They stick up at you, and also that's the shallow edited. We've also got down here a deep edited surface, and the deep edited surface is looking underneath. So you can see that I picked a particularly noisy set of data here, just to make it easier. And what we do when we want to reject data is we come over here, we go to select mode, or we can use polygon select mode, and the right over here, and we've also got an area select mode as well. If you notice, you have an A next to the area, you've got a P next to the polygon select, and then there's an S next to the select mode, and if you hover over the arrow on the explore mode, it's a space. Those values in the brackets are the hotkeys. So if you want to move around, you press the space bar, move around, press the S key for doing the select mode, the A key for the area select mode, and the P key for the polygon. So you can select your area, or select your area, and then you can launch the 3D editor. And this will just bring the exaggeration down a moment. You can also bring the exaggeration down using the, sorry, I've just got my other bits and pieces on the screen here. You've got the exaggeration window over here. So in select mode, you can use the widgets or not use the widgets, or either in explore mode. If you go to select mode, then you're now in doing something different. You're now selecting points. So if you want to move around, then you have to use the widgets. So you can select the points you want to delete, and if you make a mistake, you can clear them. And if I go back to select mode here, so what you're doing is we're coloring by line, you can color by depth. You can also color by roll, because we brought that value in. And also on the bottom here it should be heave as well, so you can color by all those. And you've also got color by sub-record for looking at the beams, and you've got colored by record as well. So you've got a number of ways. Normally when you're editing data, you color by line, because the general rule of thumb is if you see the same feature on more than one line, then it's a feature. If you only see it on one line, like here, this is just one line of data, then that's noise. So we go to then the same as selecting in Fledermaus. We have a select mode, an area select mode, a record select mode, which is quite useful if you have one rogue beam, ping rather, I'll show you that. And there's also a measure mode as well. So the mode we normally go into here is the area select mode. I'll just turn off the widgets by using the H key, and you can just drag your lasso down there, and you can drag your lasso down there, and then you can either hit reject over here, or you can hit the D key on your system, and then you can select again and hit the D key again. Go back to the area or hit the space bar, and then you can have a look. If you find you've got one rogue, I don't think we've got a rogue ping in here, but just to sort of show you, if you click on the record select, then you see it selects one whole ping, which can be quite useful. Now the real power of PFM and why it's so good and why people find it the most effective method for processing data is that when I select file and save, our area here, I need to bring you up to see what you're looking at now. The area here in the middle will be updating as soon as I do file, then save. Bang, see that area there? It's immediately being updated, and you can then go on to the next area. You can also color things by standard deviation down here. So you can. This is now coloring by standard deviation. Now, one of the things that I find really hard is if the default color map is step 16, and as you can see from the screen, that's really quite dark. So I normally go to the color map tab and change the color. Colors interpret at the top is normally quite a bright one, and once you change the color, it updates the surface, and see that's a lot brighter. What you then want to do is try and massage the colors to show more data. So if we come and if you move your somewhere down the color map, say down to somewhere about 1.5 or 1 here, and you right-click the button, and then press apply, then you're sort of bringing out some of the smaller objects. If I look over here, so you're bringing out some of the smaller boulders. If any of you are looking at sort of mine warfare applications or port security, then that's a really good way of spotting any things that you shouldn't expect to see on the seabed. You can also here notice, if I zoom in, there's a line going across which is slightly blue on here, and I can just pick up that line here, go back to the 3D editor, and what we'll find on here is that we have, see that you got, if I zoom in here, in a moment, you're going to have 3 lines, 3 pings underneath, 3 beams underneath. They're all taken from a badge selection, so we can just take the record select, take the 3 beams, pings like that, and get rid of them. And if I save and exit from there, we go back to the Fledermaus window, and you also see that the standard deviation is updated as well. So not only does the surface get updated in terms of the shallowest or the deepest or the average depth of the cell, but it also updates the standard deviation as well. So, and that's how you would carry on. You would go through and you'd isolate areas and you pull them up, and then you'd edit the data, and then after about 2 hours you'd get very bored and go for coffee. So there's a better way of cleaning data, and that's as using a cube. So I think.
Hey Duncan, can you hold on a second?
Next section? Yeah.
Sorry,
yeah.
I wanted to grab you while you still had Fledermaus up. Somebody asked if you could just talk briefly about the hide function. I think that's where you hide line or.
Oh right, yeah. I can do that. Let me just quickly fire that up.
And if anybody else has any questions about basic PFM editing now, you can ask now or later. But if you raise your hands or send me a text question, I'll get Duncan before he goes on.
Yeah. So I've got there is a rec down here which I already knew about, which I'll show you on the other one. With this one, let me I'll just clean the outside of these lines whilst your screen updates, and then I'll show you how to hide and show lines. So we're coloured by line here, so we've got 1, 2, and a little third line here. If you want to select, you can select one of the yellow lines I'm selecting here. You can then right-click and do select, and you can select the line. So that's an L if you want to do it quickly. And then if you just want to process the blue line and not the yellow line, then you can hide, and you can either hide the selected if you just want the blue, or you can hide the unselected if you want to process just the yellow line. So, so if you're dealing with if you've got many lines over a wreck or something like that, and you want to see a bit of wood from the trees, then using the hide function is quite good. And once you're finished doing your editing, you just do unhide all, and that brings it back. I'm just going to take that one sounding out. And again, save and exit, and then your area will update. So any other questions whilst I'm here on doctor killing or PFM itself or creating the PFM?
Duncan, I have a question. Does the latest version accept HTCS data?
All of the data, HTCS data has been accepted all the way back to version 5, I think, or maybe even version 6. So we've always accepted HTCS data. That's the Caris HIPS data, for those of you who don't know what HTCS is. And it comes. What you have to do with Caris insist on having their libraries licensed. So you need to have your Caris dongle, if you're using this, installed at the same time as your Fledermaus dongle when you create the PFM. After you create the PFM, you can pull the Caris dongle out and it's not a problem. But when you create or when you unload the PFM, which we'll do later, you need to have that Caris dongle inside. So if you're not seeing, when you go to select HIPS data, if you're not seeing the HIPS data path, it means that your libraries aren't right. The other thing was until 7.2.1a, there was a problem, well, not a problem, but we were using the version 6 Caris libraries, not the version 7 one. So if you had version 7 on, then you had to update your, you had to put in version 6 to enable it to be used with Fledermaus. We have found, however, that Caris have also changed a lot of their library structure at the moment. So I would hang fire on 721A until 721B is out, because they've changed the way they store variants. They've changed a number of different things within the libraries without telling us, and that's created us problems, and cube surfaces in particular are not building properly at the moment. So even though we can now read in version 7 libraries and 64-bit as well, I would wait until Anya sends out the support email for 7.2.1b, because that will then address the problems with the HIPS libraries at the moment. But version 6 ones still work fine.
One more question, and I think you're going to address this later. What does the bin size meters actually mean, and how should you select this value?
Yeah, I've got a slide on that very question, which I'll show you in a moment.
Yeah, and somebody else asked, can you talk a bit about bin size and grid values? So you can go ahead.
Okay. Right. Well, I'll just kill Fledermaus for the moment. I'll address one part that you can do on bin sizes now, and that's in DMagic when you have the lines here. If you want to see how close your data is or what your line spacing is and things like that, you can zoom into an area. So I'm zooming into to my PFM area here. I'm going to come into select here. So I'm just going to draw a small box. And then one of the options you have when you right-click in this box is the top one here, which is plot selected ungridded data. And what that will do is it will plot those two lines as just as some point files on here. Now the first thing that normally happens is the actual point size is too big, and this just does a screen refresh, so you need to sort of zoom in a little bit more, and you can put your cell size over here on the right. You can update the cell size and also show the grid. So what I've done there is I've changed my cell size to 5 meters. I've pressed the toggle plotting grid, and then I've changed my point size. When on the right hand side over here I need to replot, and that will replot the data in here. And as you see, if I just turn off my PFM so you can see the background, but if I zoom in a bit more, and then I'm just going to hit replot again once more. What you're looking at here, and I hope you can see that within the blue, is you've got this distribution of the points that you can see within the cell. So with this particular cell size, I could have gone to probably 2 meters or so here, because you're getting looking like about 20 soundings within this 5 meter bin. So this is how, if you're not sure what the size of the data set is, what the spatial distribution is, you want to zoom in. You've got one area here. You can maybe try doing, if I do done now to come out of that for the moment and turn off my PFM, you can come over into, say, this area over here, select the area again, zoom in, right click, plot again, and there you have it again. You've got the 5 meter cell size still kept the point size, and you can see here we've got a lot more points in there. So that's sort of how you see how many, you need roughly about 9 points to be able to discern an object. So have a look and see how many of these points are, and have a look in different areas, depth areas, and then you should be able to do your bin size from that. I've got another slide in here about bin sizes. So I'm just going to talk a little bit about cube processing now. This is the bit where everything starts to speed up, and cube stands for the Combined Uncertainty Bathymetry Estimator. So a really catchy title. So that's why it's called cube. And what cube is not a data cleaning. It doesn't reject data as such. It just produces the best estimate of the surface, and it gives you other potential depths for that same node point. And then, of course, it gives you a confidence interval, because if there's only one statistically valid point, then it's highly confident, and if there's quite a few different potential values, it's not so confident. So it does rely on, well, the better the error model, the better. This is the cube Fledermaus workflow, which the whole thing about building PFMs and things like that is exactly the same as the area-based editing. The difference here is that when you do cube processing, you actually edit a surface and then potentially soundings if the cube hypothesis has failed completely. So you're doing a sort of a repetitive sort of thing over the area, but mainly on the surface. And then after you've got a nice cube surface, you then run your filters over it to reject soundings if that's what you want. And then there's other options there to unload again. So these PowerPoints and things are, and the webinar thing is available afterwards, so you can have a better look at it then. So this is the cube processing now. It's sort of done in, as you build the PFM builds in the normal way. The cube side of things then does a bit of assimilation, intervention, and disambiguation, which are all very large words, which I'll explain. What happens is the first thing that Cube needs is it needs an error model. It needs a horizontal and a vertical error for every beam. And that is given by how accurate your motion sensor is, how accurate your GPS is, how accurate your tidal prediction is, or if you're on RTK, that'll make it more accurate, how good your sound velocity is. Some of these, none of these are going to change the value of the depth measurement that is in the data set. The depth measurement is completely different to this. This is calculating an error associated with that depth measurement. And that's quite an important point to remember. So all of those ones, the TPUs, we have a number of ways of doing it. I'm going to create TPUs when we build the PFM, both HYPAC and Quincy and Keras and PDS. They all create TPUs themselves, and if they're already in there, then that's a good way of bringing the data in. So you have a number of different ways to actually find the TPUs and use them. And you might have heard it be called TPE before. TPE was total propagated error, and now Brian Corder, who wrote the whole Cube algorithm, is this error means you actually know what the value is, uncertainty means you don't, so they're total propagated uncertainties now, so just to be statistically correct. So the first thing in the Cube process is to create a grid, which is exactly the same as we were doing with PFMs. So what you need, your grid spacing, is it needs to be high enough or high resolution enough to be able to capture the features that you actually want to see. If you want to see a meter boulder, then you need to grid it at the minimum is a meter, if not half a meter, so you can see that meter boulder. And then of course you need the sounding density to be at a level that you can actually grid at half a meter. So there's a number of issues even before you do the surveying that you have to work out. If you need to look at what size feature you need to see, and then you can set your line spacing. You can look at it in real time to make sure you're getting enough soundings at the same time. There's a lot of information that you need to, once it comes into the PFM, the chances are the boat's somewhere else, or you're all demobbed from the boat, and that's too late. So this isn't just a PFM issue. This is a survey planning issue as well. However, there are a couple of things that we do. These are some. I'll explain capture radius when we in a moment. But these values here as basically, if you think of 0.71 times the cell size, what this is doing is giving you a little radius around the node, which captures everything within, say, that 1 meter bin, and goes slightly outside, but not too far outside, or else you start to smooth your surface, which is not what you want to do. So a capture radius of 0.71 times whatever cell size you choose is a good value for putting into here. One of the issues you might find is with sonars that don't have a particularly high ping rate and you're in very, very shallow water. If you leave it, the default is normally 5 times water depth, and so if you're in 1 meter or 0.5 rather times water depth, and if you're in 1 or 2 meters of water, that's not a very wide capture distance. So you end up with a perforated surface rather than one that you should have. So this is an example of if the surface is, this is 10 meters from here to here. If you had that, these would be the node values. You'd completely miss out this feature in the top here. If you have it at 1 meter spacing for the node, then you capture all the information. Well, that's 5 meters actually, but yeah, you get the picture anyway. You need to have the right size cell spacing to capture the feature. So it's feature really dependent. So once the data is coming in, it's looking at the data, where it's from, where it relates to the Cube node, so whether it's within this capture radius or not, and also what the uncertainty is as well. The way that Cube works is that each sounding has a horizontal and vertical error, but that is assimilated into just a vertical error at the node point. So the further away from the node is, the higher the uncertainty as well. So you basically have no horizontal uncertainty because you know exactly where that cube node is, but you do have a vertical uncertainty dependent on the soundings affecting that. And also this is so this is one, the capture radius, but also the further away from the node you are, the error, you can decide how fast that error degrades and whether or not it's going to be used in the cube calculation. This is basically what cube does, is it doesn't reject data on the way in. On the left here we have an estimated position depth for the node. We have a predicted position in the middle here, and then the sounding comes in here. It's within the prediction. The uncertainty is also within the prediction, so it just updates the estimate based on the new one. It does this for every sounding that comes into that node. Over here on the right, we have the prediction. Over here, the actual current estimate, and then 4 times the standard deviation here, or greater than 4 times in this case, the sounding comes in, which is now not affecting this at all. This is almost a completely separate depth estimate. And rather than rejecting it, it just goes, hang on, this is a new one here, we're going to start tracking this one. So it will track this estimate and it will track this one. So now you've got 2 potential depths at any one point. And it will keep doing this until it gets to the end, and every node now has, you know, a variable number of potential depths for it. So in this example here, this is one node. We have one set of depth data at about 13 meters down here, which has got a lot of samples, because this is the number of samples with it. So this we also have another node here. We have another track up here at about 3 meters, which is probably aeration in the data up here. So it's not rejecting any of these. It's all tracking them, and then it says, this is what the disambiguation is. It says, okay, I now have all these different estimates of what the depth might be at this node. Now let's decide which one is the one that Cube is going to take, and how Cube decides that is based on what you select. The number of samples is normally the one that works best, so the popularity contest, basically, who has the most wins. You have one which is a neighborhood, so it looks in the neighboring soundings cells, and whichever one of these values here is most consistent with the neighboring one is selected. You also have a combination of the number of samples and the neighborhood, and then there's a predicted surface or average surface as is used, and whichever one is closest to that average is used as well. So the thing about Fledermaus is you can choose any of this later on. So you know, your decision you make about it now does not mean that it's going to be the same decision you make later on. And then the output is basically, we have a depth estimate, we have a uncertainty surface, we have a number of hypotheses, so that's a number of potential depths at that location, and we have a hypothesis strength. Now if you look at these 4 images here, you can all see that they point to the same part, basically. So, and this is a big thing with Cube. The bits out here in purple on the bottom left here, visually as well, you can see that it's you know, it's good soundings here. The same with the hypothesis strength, same with the uncertainty. There's absolutely no point looking at any of the soundings in that area. You only need to look at the soundings which are being highlighted, and that's the big saving in Cube. So what I'm going to do now is select our soundings here, or our lines. I'm going to create another PFM, so I'm going to build a PFM from here. I need to unselect my lines for the moment. So if I go down here, select my lines, and I'm going to right click in here again, build PFM. This time when the build PFM dialog comes up, there's a tick box at the top which says use auto processing Cube. Again, it knows that our data is WGS84, our project is UTM30. The bounds are the bounds I've just set. The bin size, I had 4 before, I'll use 4 again. The Z range, again, remembering what I said about if you're adding data to this later on, then make sure that the Z and the XY ranges will encompass all the data. The vertical resolution is the same. And now when you're doing cube, this previously grayed out box is now open up. And these are the settings that you can make in Fledermaus to control how the cube goes. Now, percentage of depth will work fine in deeper water. If you're going in shallow water as well, then we tend to use a fixed distance. And this is where you do that times the cell size. So 0.71 times the cell size. Actually, on this one, I'm going to use percentage of depth because this will work okay. So 5% of the depth. The next one down here is the cube hypothesis. So this is now when it comes to making the decision as to which one is going to win, then we can choose one of these. I'm going to choose predicted surface for the moment. Now these two are quite, well, this one in particular is quite crucial. This is the estimate offset. This is telling you how many times the standard deviation is going to create a new, it's going to look for a new depth node. So 4 times the standard deviation can make quite a lax judgment on it. 2 times, so an estimate offset of 2 will produce you more nodes but a tighter cube surface. The horizontal error scale here is how quickly those soundings degrade from the node. 2.95 is the default. You can have 1.96 or even 0.5. This one doesn't make anywhere near as much of an effect as the estimate offset. So 2 is normally what we normally choose for estimate offset. Now this is saying, okay, you wanted to do cube. I need TPUs, horizontal and vertical errors for each beam. Where am I going to get them from? If you have the data now, GSF has got fields for horizontal and vertical error, but I know that those are 0 in here, so that will give me no cube surface. You can, if you've got historical data like a single beam data or something like that, and you just sort of guess the horizontal error accuracy, you can use that here. Or if you've got XYZ ASCII data, you can put the values in here, which you think is going to be the case. If you have data which is already like met IHO Order 1 surveys, and it could be single beam, could be historical, multi-beam, then you can select that. Be careful with this one, especially with multi-beam data, because the horizontal error, horizontal accuracy for IHO order stuff, and even the vertical one, is pretty loose. So this can actually give you quite weird results that you don't expect. What we're going to do is actually calculate it, and we're going to calculate it ourselves in the PFM build wizard. The sensor type we're going to use is the resonancy about 8125, because that's what this one is. And then I already have a PAR file. You can actually find one of these. I've got the wrong place. No, I know where it is. Is it this one? The PAR file here is it's just a text file, and if you can look at it, and I'm not sure if you can actually enter stuff in here. No, not quite yet. But this basically, you fill this in with where the IMU is in relation to the transducers, how good your sources of various offsets are. I've got 0.3 of a meter in here for our GPS accuracy, because it was using a CNAV system. I've got 0.1 for the tide measure. The GPS, by far and away, the two that make most effect on the TPU values in your cube solution are the GPS accuracy and the tidal error accuracy. It's both measured and predicted. It's, if you have this set at 1 or something, then you're gonna you're uncertain. Your soundings could be spreading over plus or minus 1 meter. So the cube won't give you a very good solution. So put those down to some as tight as you go tighter rather than looser, so more accurate rather than less accurate on these measurements. The other ones are really just some of them are like operator specs. There are some software packages that will say if you're using a Planex's POS-MVs and you're using POS-Pack to process the data, they also have an RMS file that goes with the SVET file, and you can load that data in, and that's the actual POSNV position, roll, pitch, and heading accuracies that it actually creates from the Kalman filter, which is obviously a better solution than these. So once you've selected the sonar, once you've selected the path file, you do next. I'm not going to bother setting a custom filter on this, and then I'm just going to call this 8125 cube. And this will add the files in exactly the same way. This bit is exactly the same as before. There's no difference here. It will then create the cube hypotheses after it's done the normal initial PFM build, and then the cube surface, and then it's all ready. So whilst that's building, any questions on cube theory or how to build stuff?
Hey Duncan, there is one question, but before I get there, it is 11 o'clock and obviously we're going to go over, we're going to let this go through, so if you have to leave at any point, you're free to leave, but we're going to continue it out because there's a lot of interesting stuff to talk about. I did have one question. How, as in how well and procedurally, does Cube deal with uncompensated motion, especially roll?
It treats it as being the problem with something like that is that Cube is not going to back out any motion artifacts in the data. It doesn't. It will show you where you've got them because the uncertainty will be higher, but it won't actually create back those out. You have to do that before you bring them in here.
We have another question. I don't think you will answer this one. Well, I think you can sarcastically answer. How soon after a new multi-beam echo sound or sonar arrives in the market is it included in the Cube sonar list?
Not very fast, but we do need to support more in our own one. We need to support more of the models. Some of the other, specifically the acquisition software guys, most of those have got good models for doing the for the cube process. It's not really going to have huge amounts of effect, but you need to have the right number of beams in there and things like that, or else it has various issues. So they should be, they should be out within a few months, but also it depends on. I mean, if the sonar manufacturers made them, I'm not sure what the format is, but if they made them, then it would be easy to incorporate.
And I think I have one more question here. Hi, any recommendation for data with problems with the sound velocity corrections? Any way to make overlaps between lines look better? Thanks.
That's a good question. The answer at the moment is there aren't any tools to do it. We have quite a few things in development. One of them being this PFM at the moment. The next generation is going to be more of a tile-based structure, so you can hopefully we'll have multiple resolutions and things like that. And one of the things we might try and do to work with that is to be able to back out what the sound velocity should have been and flatten it out. But it's not a trivial thing to do. I mean, there are, if you can afford it, there's the ODIM moving vessel profilers that will profile as you go along. So ideally, you don't really want to have the sound velocity issue, but yeah, there is a need for having it something that can do that in some ways.
All right, Duncan, I think that's all of our questions for now.
Okay. Whilst that's building, I'll just show you the cross-check. I won't actually show you the program. I'll just show you what it does. This is an application within the Hydro Suites and FM Pro, and it's very simple. It does exactly what it says on the box, and it's a point versus surface comparison. So the idea here is you take your final cube surface Now, bearing in mind, this should not contain the cross-chat lines. You should keep those out of the surface. So it contains the all the lines other than the cross-chat ones, and it should be a good surface. And then you take your cross line or cross lines. You can do multiple lines here, and this will take in all the different file types we previously shown about what you can do in a PFM, and it will compare each beam to the surface at its position, and it will create what's on the screen here as a depth error distribution. This one's a nice Gaussian curve there, so it's showing good correlation. And down on the left here, once you press the analyze button, there's an analyze button here. Once you do this, it will also say order 1 test accepted, order 2 accepted, special order accepted on this one. So so this is what you're looking for. If you're doing an IHO order 1 survey, then that's really what you want. You can save the statistics down to a text file, and you can also you can just screen capture what I've done here and put that into a report too. So this will also give you the range of the depth differences there that you had. And if you look down the bottom here as well, you might just see it says multi-thread setup. We're gradually making more and more of the applications multi-core capable, and cross-check and FM geocoder are both multi-core enabled, and so is FM midwater too. And the next version of PFM and the gridding algorithm and everything, that will all be multi-core enabled when they come out. So rather than loading one file at a time like we're doing at the moment, you can load up to, in theory, 12 files at a time. You'll also come across hard drive bandwidth issues when you start doing many cores like that. But that should make a substantial difference. So these are the results. This is from another survey here. So you've still got the order 1 test accepted. There's a bit more of there's obviously a couple of flyers in this one, so the curve is tighter, but it's still the same. And this is what you then stick in the report. So this is the data QC on you launch cross-check, you load the reference surface, which is the cube surface normally, you import your cross lines, you run the comparison, and you analyze the results and screen capture the things and save the statistics down for what you need. Oop, there we go. So our build's complete. We didn't have any XY filters or anything else, it's all there. So, so I shall then go to Fledermaus, and I shall open up my SDs. So I have my cube surface and my PFM here. I'll just change my color map quickly. This is the same area, so I can extract the area. So this is showing you the shallow editor surface. Now this is a cube editor surface. So as you can see, it's done quite a good job already when it's doing it. What you can see there's still quite a few areas where it's giving cause for concern. So rather than just going, okay, well I better go and sort these out, you can sort of go, okay, well let me try something on a small area. So I've just selected a small area of this, and down in the tools and the cube options here, there's more cube options down here, and you can say, okay, well predicted surface gave us this, so that's not particularly good. So then we go to number of samples. If you needed to increase the capture radius, you can increase the capture radius, and the SMOS output. I'll do it again there. And then for a PFM, you can do everything on a selection. So if I go to Tools, Cube, and Recube, you can do it on a selection. You can do it on a loaded area of the entire PFM. So I'm going to do it on this selection here, and you can see just by changing the way that the cube algorithm, how the cube decides which is which, you've just saved yourself a fair bit of effort in doing the data cleaning. And if I select this area here, and then just do Tools, Cube, Recube, Selection, go. It's a slightly bigger selection, but it shouldn't take too long. I'm hoping. Yep. And you basically, you've got that surface pretty much sorted. Now, to show you how the cube actually looks and works, if I select this spike over here, I launch the 3D. So these are the soundings again. You can see this is some gas stuff, and then over on the right here you've got sounding editing. So we've got a cube editing, and you have where the cube has decided it is, because of the number of samples, it's got a big square. Where the cube thinks it might be, but it's not, says it's not the right one, you've got a little square. Now, because you've got the right answer, you can just come over to this square, you can select the square, and then you can just do, remove my thing, just override, and then that will override what the cube solution says, and save as an exit, and lo and behold, your cube surface is updated. Now, that's what you do if the cube has got the right solution. If I take one of these bits on the edge here, and I launch my 3D editor, there are some points here where the cube hasn't got the right answer. Actually, I think most of these have got the right answer. Let me just, what I've done there is select connected, so you just hit the L key, like selecting the line, and then you can just override all of them in one go. But yeah, down here, see, there's only bad values down here. There's no good value further up here on the surface. So what I'm going to do here is I'm going to have to go back to sounding editing to get rid of the road flyers. So I can select those soundings there, and I can select these soundings here. And now when I save, I can go back to the cube. Then we have a better selection of the soundings. It's updated the cube surface based on those. So where the cube fails because there are no good soundings, only bad soundings, you have to reject the bad soundings, and then you get the correct surface. Now, when we're doing this, that's the only time you're rejecting soundings. If I go back to shallow edited, you'll see that all the spikes are still there. So we still have the spikes in the data. So you work on that cube surface until you have the cube surface absolutely perfect, and then you select. You can do this on an area first just to make sure you're getting the values right. But what you're going to use now is you're going to use a cube surface to filter and to reject the soundings which are above and below a certain distance from that cube surface. So the way we do this is back into Tools and Cube Options again, and then we go to Filter Soundings, and we have a few options here to filter, and we also have the ability to do it on a filter above and below at different amounts. So we can filter based on the standard deviation. The problem with that is if you've got very low standard deviation, you've got really good data, then the 2 times 0.05 is not particularly a large distance, so you end up deleting soundings you don't want. If you're doing on meters, you can find that over rocky areas, it's not expanding enough, so it's cutting the tops and bottoms of the rocks. So what we tend to do is do it on, say, 0.2 of a meter, but then say 1 or 2 times the standard deviation. So the minimum distance is 0.2, and then there'll be whatever over the standard deviation above that. And if you want to go really tight above the cube surface and looser below the cube surface, specifically if you're doing nautical charting, then you click the Apply Different Filters option, and you have an option to apply different above and a different below one. We'll do the same for both at the moment. Then the scope is on the selection here again, because you just want to try it on this area, and the action is to set the rejected flag. So we can filter, and there you have it, the data set updates, and that's where you do most of your data cleaning. If you're doing over a rec, then if I take my rec here, launch my 3D editor. Over a wreck, the best thing to do is to manually clean the soundings around the wreck. So that's going to take those in. Then if you have a lot of wrecks, then the best thing to do is we have an option over here to select the shoaless sounding, which then selects this one up here. And then you can right click on it, and what we want to do here is you want to edit this, and then you want to set this as a feature. If you have a lot of wrecks, I'll explain if you have a lot of wrecks. If you don't, if this is just one wreck, you go to the cube option, and then we're just going to recube in here. It's going to ask me if I rejected point, so you want to save it first and say yes. So on the cube side of things, we want to make sure that if this is for a charting server, you want this to be navigationally safe, so you want the DTM to actually follow the top of the wreck. And the easiest way of doing that is to select all the cube hypotheses here, and then here you can select them and move the selection up. And there's a hotkey for doing that on the keyboard as well, and you keep doing this until you're at the top, and then you press O for override, and then you have a navigationally safe DTM. If you want to make absolutely certain you've got the top of that wreck, if you go back to soundings, you've got your shoaless one selected, you can right click and do set custom hypothesis, and that says I don't care what the cube says about the depth here, the depth of this particular point is the depth of whatever node this sounding belongs to. So if I zoom in here, it's now at the depth of this particular sounding, so which is good. If you have, what I said, if you had a lot of data, a lot of soundings, a lot of wrecks, if you do the feature flags, and then at the end you can use this option to create hypotheses from features, and that will just take all the feature flags and it will send a hypothesis, create them to be a custom hypothesis. And the same is over, of course, don't forget about shoals as well. You want to come in here and say, if you're really worried about the depth on these things, then manually clean the data around it, so make sure you've got the right data out. Then you do the select by shoal, and then you can do set custom hypothesis, or you can do F for the feature, or edit set feature. So that's where you have your cube, and then you basically run the cube through the filter the soundings through that cube surface. So then that's where you do most of your dot killing. There are also tools under the filters here if you need to run plotted sounding selection. You can set the scale of the chart, and you can the minimum distance, and that will select the shoaless soundings, which you can then export. And then also if you're doing like oil and gas surveys and you just want to process Bathy quickly, you also want to, if you do tools and create surface object, then up here you now have just a DTM, which is you can use for anything, for draping the imagery, for anything else in there. So so that's cube processing. Any questions on that?
Does anybody have any questions on cube processing before Duncan moves on? You can type, or if you want to just raise your hand, you can do that. Just give it a minute. I am not seeing anything, Duncan, so go on ahead.
Good. Excellent. Right. The only things I was going to do is you can do a chart comparison here. What I need to do is bring in a chart, which is, and in the UK here we get charts from the as geotiffs from the UK Hydrographic Office. So in my project I can add an image, I can add a file, and my source images. Here's my chart. The UKHO charts are quite specific. There's central meridians down the center of the chart. So when you add that in, this is where that image is going to go. What I will also do is quickly edit this image because I want to just have a cropped image. But because this is a specific georeferencing, I just need to reproject it first. So I'm going to reproject the image from its weird one to the project coordinate system using the reproject button. So this will now put the image in UTM zone 30. And then once I've done that, I'm going to crop out the small area where the survey area is, and then we're going to use that. So that's been done there. I'm just going to crop out something about there. So I'm just going to select an area there, then do crop, and then do save as. And this is 0154 UTM crop. So then I'll close my editor here. And then, so this is the bigger image. This is the one I've just created. And then I'm just going to make it into an SD file so I can load it into Fledermaus. So there's our chart. There's our lines. So if I go back here, I'm going to open up my SD file. So here's my chart. Here's my data. It's 3D, so you can't layer things because the data's there. What you don't want to do at this stage is mask out areas. We have this option where you can mask out the areas and it will see through to the image. You don't want to do that at the moment because you won't be able to drape it down on top. So what I'm going to do is just take my PFM surface here, come down to Tools, I'm going to drape image on surface, select the loaded SD file, and I'm going to apply illumination to it so I can see the seabed features. And this is going to be at 4 meter. Let's do OK. And then now you have your draped image. And you can see, oh, no, there's a rec, and there's a rec symbol on there, so that's definitely a rec. If that rec was there and it wasn't on the chart, then there'd be issues. The other thing you can do is, this is the 50 meter contour here. We can check to see where it is now, so we can do Tools Contouring. Oops. Let me just select that option, Tools Contouring. And then I go Insert a Contour at -50. This is our now line. I'm just going to change the color so you can see it. Make it a little bit wider. So you can see on here that the chart's not that good. The 50 meter contour is actually a little bit shoulder. It's an easy way to see movement on the seabed, and then if that's navigationally significant, you need to send that in. The way that I drape the chart, the Tools Drape Image, you can use that for doing backscatter as well. If you want to bring the chart back in, but now you actually want to see through it, we need to mask out areas box. We need to Tools Compute Mask first. What this does, it looks at the DTM, it looks at the image, and the overlapping areas with the image, it says they can be made transparent. So that's what you have now. So there you have the image and the chart together. So the last thing that I'm going to show you is, and I shall demonstrate it first. Well, I'll just demonstrate it, it's probably easier. And this is how to get the data from here out. What happens next to the data? And we have two ways of doing it in Fledermaus. One way involves the Atlas Oracle database solution, where they actually take our PFM and take that surface and take the soundings into their Oracle database, which is then used by the 7 Seas product to create the ENC. And the other way of doing it is sending the data into an Esri geodatabase. And for Arc Editor, Arc View, and Arc Info. It doesn't have to be for nautical charting. My reason for being up here in Aberdeen is for the Esri Petroleum User Group meeting. So that's all oil and gas. So you can take all your surfaces, all the imagery, and push them contours and push them straight into an ArcGIS database. And just to show you how to do that quickly, we create an ArcGIS workspace. You can either connect to a database or you can create a database. So I'm just going to call this Falmouth. And then we connect to it. And then what we have here is, if I click on my 8125 Cube PFM, we have ArcGIS buttons now. We have ArcGIS buttons in a lot of places, but we have the option here to transfer those plotted soundings if we did them, transfer the bag, which is the the cube surface with uncertainty, transfer the survey area, the Bathy raster, and the image raster, or in a transfer wizard you can do it all in one go. You select the database and then you press OK and it will send them all to that database. If I look at this one here, this is, I'll bring this one out. This is one that I've done earlier as such, and this is an arc map now. And the points here are the plotted soundings. You can then also have, you have the image raster. You've also got the Bathy raster that you can work with, and you've got the areas, survey area as well. So you have all these different types of data which you can then go and analyze and do everything else with. So I'll go back to Fledermaus now. Are there any questions at all on anything that I've covered today?
Hey Duncan, I have one question. It's not really related to Fledermaus, but maybe you'll know the answer. Do you know how much the geotiffs cost from IHO of the charts?
From the UK Hydrographic Office, it's hard to get them. You can get them via C-Zone, I think, and you can request them from UKHO. Basically, we get them. You can get them as part of a survey if you're updating their charts. They'll give you the charts for free, the geotiffs. Best thing to do is email them and ask, or C-Zone, which is I think czone.co.uk or czone.com, and you can get them from there. But I don't know how much C-Zone charge.
Okay, here is the question, and I'm just spitting these out at you as I get them, so they may not come out very nicely. A question about gridding data in DMagic. When gridding ungridded files, you specify cell size and also a weight diameter. Can you explain what shape the weight diameter has? Is it a horizontal area? Is it measured from the center of a cell or from the edge?
It's measured from the center of the, well, basically a weight diameter of 3. If you think, I'm just trying to feel I've got an easy way of looking at this. Yeah, I can probably do it in here. Let me just turn a couple of things off. If I go in here and do my plot points, okay, if I zoom in here now, if I do a weight diameter of 3, you can see you've got the square here in the middle. If I zoom right in there. So you have a weight diameter. This is if a weight diameter of 1 will only take data within this one cell. A weight diameter of 3 means it's a 3 by 3 cells. So it will take data from any of these 9 cells here, but the further away from this node here, the less influence it has on the data. So that's the cubes one way of doing it is that it will have this capture radius which will go around the outside of this cell, and the further away from there, but it's not just a distance, it's also the vertical uncertainty of the point and horizontal uncertainty of the sounding, because it will prioritize the ones with a lower error than the ones with a higher error. So the cube way of gridding, if you like, is more correct, but the weighted moving average is also quite a good way of just gridding the data. A 5 by 5 would take in a 5 by 5 cell, or weight diameter of 5 would take in a 5 by 5 cell, which is generally too much, and you end up smoothing the data. So 3 by 3 is the default for a weighted moving average, and that's the 3 by 3, the weight diameter of 3, which is 3 by 3 cells.
All right, thanks, Duncan. Any final questions? If you have one and you can't type fast enough, you can raise your hand. If not, give it a minute, or less than a minute. All right, Duncan, I think you're done. Thank you very much. Thanks, everyone, for attending. Like I mentioned, this has been recorded, and if you are a client, you can request the download. Thanks for coming, and hopefully we'll see you all on another webinar in the future. Thank you. Hi, this is Erin Heffron from IBS 3D. I'm recording this as a bit of an addendum to our 11/17/2010 webinar, which described and demonstrated PFM processing and cube processing in Fledermaus. We forgot to talk about the final step of that processing, which is called the unload, which will apply the edits from the PFM back to your original source data. So I'm going to step through that unload process now. So you're in Fledermaus, you've just done your editing. Either you've done area-based editing where you go through and reject points, or perhaps you've done cube editing where you validate a surface and use the cube surface as a filter, or maybe you've done a combination of both. But at the end of the day, you have a nice surface here when you view it in Fledermaus. When you're in Fledermaus, you'd want to go through and just have a check at the surfaces and make sure that you've edited everything completely. So right now I'm looking at a cube edited surface, but I've run a filter on my cube surface and rejected all of the soundings outside of the cube surface. So if I go to my shallow edited, it should be pretty comparable to the cube. So I'm just going through and looking for anything I might have missed. And then I would go and look at the deep edited. And again, shallow edited will show you the shoalest sounding, so it will be outliers on the top of the surface. If you go to the deep edited, you're looking for any spikes below the surface. So I would just scan through underneath my surface and look for any low spiking that I might have missed. Remember when you're looking at these surfaces that the edited options, shallow, cube, or average edited, depending whether you ran cube or not, and the deep edited will always reflect all of the changes that you've made. The top three will always be the original data, including all of the errors. So for example, if I go to the shallow surface, that's going to show my data, the really dirty version of my data before you did any editing at all. And the deep will show you all the bad noise that was underneath. Alright, so don't look at those when you're validating your surface. You want to look at one of the edited options. So I've checked my surface, everything looks okay. The next step is to close Fledermaus. All of those changes have now been saved in the cube surface, in the PFM. The PFM has been updating as we made changes. So we close Fledermaus, and you're going to open DMagic. If you don't have your DMagic project open where you created the PFM, you would go to File, Open Project, and load up the project where the PFM was created. So in my project, I have the original GSF files that we used to create that PFM. I have the Falmouth PFM here, and it's listed down here as well. To do the unload, you just go up to Tools and Unload PFM. Under Select PFM File, you're going to browse, and in your project, so my Falmouth UTM project, you're going to select the PFM. With the PFM, there's two places where it's stored. It's stored in the SD folder. A PFM SD is created, and that's my PFM there. And it's also stored in the PFM folder itself. I can also access the PFM using this file. And these two files are exactly the same, and they both work together. So if I choose one or the other, it's not going to affect the unload process. I'll just go back and select the SD, but again, it doesn't matter. Stay open, and then I click Next. The next is how you want the PFM to be unloaded, and you don't really have a choice in this matter. If you have a multi-beam format file, a GSF file is an example, or an HS2 file, those files will unload by applying the edits back to the original source files. So any edits you made in the PFM will go back to these GSF files, the original files. There's a space in a multi-beam format file that allows the flag marking a sounding as rejected to be turned on, so to speak. If you have an XYZ file that you created a PFM from, you can't unload back to the original source files. XYZ files don't have the space or the file structure to allow you to apply this rejected flag. So when we unload an XYZ file, we unload by saving, and it will create a whole new file. it will have the same base name as the original file, but it will have a underscore edit or some other marking at the end of it telling you that this is the clean file with only the accepted soundings. And don't forget, when we do this, when we do the original, apply edits to original source files, we're not deleting any points. We're just marking them as rejected in the original files. They're still there, they just won't show up in any of your surfaces, and they're marked as rejected. So you click finish and it's going to start unloading. This usually takes a little bit longer, but I only made a few edits here, so it didn't take very long at all. At the end, you get this little sign that says the PFM unload is complete. You say OK, and what it's going to start doing, you'll see your lines will turn red over here, and that means that they aren't scanned in yet. It's really reading the metadata for those files because the metadata has changed. There's some points that are no longer part of the file. They've been marked as rejected. Once they all come in, a way that you can validate the PFM unload is to go through and grid the surface using the shoal bias algorithm and the deep bias algorithm, and that will confirm that all of the outliers have been rejected. So I'll go through that once the scanning is complete. Alright, so all my lines have turned black over here, and that tells me that the metadata has rescanned and these files are now updated. So to confirm that the changes were applied to the original files, I can click on the GSF file up here, right click, and this time instead of building a PFM, I can grid ungridded files. So I'm going to just go through the gridding algorithm. You leave your projection information. The original data was in WGS 84. We're going to zone 30 north because that's what my project's in. I want to change the gridding type to the shallow bias, and this is going to make a grid of the shoal-less sounding in every bin. And that will show me if there's any remaining outliers. The weight diameter doesn't work for shallow bias. It's not part of the shallow bias algorithm, so you can ignore that. And I'll set my cell size to 4. Click Next. I'm going to keep the default color map, and I'm going to call this Shallow Test because I'm just using this surface as a confirmation that my unload worked. Click Finish, and it's going to go through and grid those files. Alright, so it's gridded the surface, and I can take a look in DMagic and see if anything really stands out here. Or I can just open Fledermaus. So I'm keeping DMagic open. I'm going to open Fledermaus. And I'm going to load the new SD that was created. So if I go into Fledermaus, File, Open Data Object, and within my Falmouth UTM 30 North project, in the SD folder, I'll find this new Shallow Test SD. I open that up and then take a look. I'll see that this surface is clean, so there are no outliers, and that just tells me that the unload process worked. I got rid of all of the outliers that were visible in that shallow surface that we looked at. And then as a final test, you might also grid it as a deep. So again, selecting all the GSF files, right click, grid ungridded files, step through again. And this time, select the deep, and that's going to take the deepest sounding in every bin and make a surface out of that. And again, it's going to let you check to make sure that all of the deep outliers are removed. The final test you could do if you are really doing some very thorough QC of your data, you can go through and rebuild the PFM from the data, and you should see that all of the soundings that were rejected are, again, rejected. That would take a little bit of time, but that's probably the final test that you could do. So that's it. That's how you finish the PFM processing. Thank you very much, and enjoy.